So, einen haben wir noch. Es freut mich, Jörg begrüßen zu dürfen. Wir haben uns gerade erst kennengelernt. Er hat eine CMDB wirklich fürs Monitoring vor allem entwickelt und da bin ich schon sehr, sehr gespannt drauf. Viel Spaß.
Thank you. So, hi, my name is Jörg. I'm from 1&1 in Karlsruhe, and I work as a senior Linux admin in the monitoring and infrastructure team on the monitoring side, and we run services like the 24/7 NOC service desk, incident management monitoring system as a service for other internal teams in our company. And over the last year, 1.5 years, we've redeployed and rebuilt our entire monitoring stack. And I'm here to present one part of the software that came out of this. We'll go slightly over the previous system, where we came from, then how we set up the data model, how the rollout workflow works, and then the present-day system that we are running right now, and how we plan to expand it in the future. So this was our previous system. Installation time frame was around 2009, 2010. It was already monitoring as a service. Admins could access an inventory system, say they want to check, which then gets provisioned in the monitoring system. And our 24/7 operator desks accessed it over the front-end console. And also we have a lot of monitoring systems because we have a lot of servers. So they also needed to access that, so our on-call duties could be dispatched from a single console. We provided remote monitoring, local monitoring via an agent. And the backbone itself was rebuilt in 2011 for geo-redundancy on a structured log replication basis, similar to what you nowadays find in Apache Kafka. But we weren't entirely happy over the years with them. There were a couple of understandable decisions that were made, which didn't work out with how the industry developed. So what we didn't really like, so the system was a proprietary system with a proprietary configuration interface. So the adaptability for us was very limited. It was integrated with a single inventory system, our data center hardware inventory system. Nowadays it's mostly VMs, or it's still a lot of hardware, but it's also a lot of VMs, which the hardware inventory system doesn't register natively, let's say it that way. So we also had limited automation opportunities, and the system could only configure the one proprietary monitoring system. The system also came with a custom agent that was running on the systems. And basically, if you went into the inventory system and said, I want to create a check that does something locally on the system, then the monitoring system actually pushed the executable that would do that onto the local server. And we as a monitoring team, we didn't like installing executable software on other people's machines, especially since it sidestepped every standard deployment workflow we had in the company. There's no patch management, no deployment audit trail, what is running on what software. It wasn't easily queryable, if at all. So this was also something we didn't like. We had here this alarm API, which is basically a JSON post interface that creates alerts inside this monitoring system, so every other monitoring system can pretend to be a probe in this one. This was a custom edition from us, also around 2011, 2012. But as it was a custom extension from us, the capabilities of what we could do with that API was very, very limited, because we had, of course, to adhere to the data format of the vendor. And lastly, the front-end application for our permanent shifts, we couldn't really update at all, customize. So if we take all those identified issues and apply them to the system, there's really not that many parts left that we were entirely happy with. What worked for us was the alarm API, and what really worked for us was the geo-redundancy synchronization via replicated logs. This was something we very much liked and wanted to keep. So we looked at what we need. We need a new local monitoring component. If possible, not yet another agent on the server. And also we wanted local configuration rollout via pull. The old system was push, and if you try to push to 40,000 servers, 12 of them are not online. 5 have a full hard disk, and 2 have been shut down last year, but you didn't get the memo. So a pull-based approach is much easier. Also, pull you can pull every 1 hour, but you can redeploy and pull again. But the push will only come once. So this was very important for us. Remote monitoring, well, we needed high availability. We needed multiple data center locations. We needed location-aware monitoring configuration rollout. So if you have a check for a server in somewhere in Middle America, in the Midwest, you don't want to check that from southern Germany. You want to run the check in America as well. And something that is often problematic with a lot of monitoring systems, we need support for asymmetric networking. So most monitoring systems assume if one monitoring node can access that server, then every monitoring node can. And we have a couple of thousand VLANs, a highly segmented network over all the data centers. So just because one server can reach that resource and monitor it doesn't mean that the other parts of the system actually can reach it or should be able to reach it. And this is a big problem with a lot of monitoring systems. If they have a high availability options where they can migrate the checks to somewhere else, they don't know what is reachable from where. Then, of course, the next role that we needed to accommodate was we needed a central notification system for our on-call or on-site teams. So we split the monitoring and the notification aggregation maybe into separate systems. We keep the alarm API because we liked it, and by keeping the alarm API with a backward compatible format, we don't actually need to migrate all the other monitoring systems, but instead we migrate where the same API leads to. We of course need improved automation capabilities, and we wanted to keep the monitoring as a service aspect where we provide a self-service where other administrators can say, I want this and that monitoring from you for my servers based on system-defined capabilities. Not every monitoring system that is attached can do the same things. And of course, user permissions. So what we came up with and what was pretty clear at the time was we need a configuration service middleware. We need a scriptable CLI. And then we want to import from external data sources instead of referencing them. So by importing all the data that we need, in the disaster recovery case, we know that we have all the data we need to restart the system. And if one of the external sources changes, a new inventory system, we only need to update the importer. And of course, this also accidentally means that we have to provide a full API layer, so everything can be modified by an external tool. And importers can, of course, be implemented on top of the CLI, since the CLI is scriptable. And we want to support an arbitrary numbers of monitoring systems, not just one, and for the same monitoring system, also different versions if they have any incompatibilities, which meant, okay, we will probably need to go with a generic output format instead of trying to re-implement and keep up with every monitoring system that is out there. So let's build a configuration service, which brings us to our data model. Simple objects, no optional fields, because you want to create a service. Here are the 750 attributes that you can possibly select, and we think those are enough. Those lists are always outdated. They never survive half a year or something like that. Our previous system allowed a tree-based organization, which a lot of people liked until they realized there was no inheritance. So it only looked fancy, but it wasn't. So we wanted to provide inheritance, but not mandatory, but an optional feature if you want to use it. Our basic object types are the configuration repositories, buckets, and nodes. And these are also the global objects. So the repository is the root of a configuration tree. It's also a concurrency border in terms of job execution serialization. And if a team of administrators has a repository, it can partition it further into buckets. And then we have the nodes, which is in our case simply a generic execution environment, whether it is hardware, VM, jail, container, zone. We don't track how the execution environment is actually running on the physical hardware. If there's 1 layer, 2 layers, 3 layers in between, we don't track that. We only track on which physical hardware it is, so we can get the data center location back from it. And these are, of course, global objects because we import them from other sources, so we can't have them multiple times. We also have advanced object types, which is a cluster which allows to group nodes. And these are actually unique for bucket. And we have groups. And groups allow to group basically everything except itself. And the main difference for this is that for clusters, so clusters can do nothing that a group can also do, but a cluster gives us the assurance that it only contains leaf nodes and no arbitrary deep additional trees. And here is one example how such a tree could look. We have a repository, a bucket, then 3 nodes directly attached to the bucket. We also have a cluster of nodes, and we have a group that contains 2 clusters of nodes. All very nice, but as we said, all the objects are very simple and have only the minimum amount of keys that we really couldn't do without. So this is actually not that expressive. And for that, we introduce properties. If you are familiar with ZFS user properties, this is basically stolen from them as a concept. They are runtime defined. We are the CLI. The moment you define them, they're ready to use. They support inheritance, and they are assigned to an object in a specific view. So you can say, this node has this property, but only if it's checked via the external interface or the internal interface, or if you reference it from the management interface, iDRAG, all that stuff. And then we have the property types. We have system properties, custom properties. I'll explain all of them in the next slides. So a system property is a simple key-value pair. It's globally available to everybody, so it's predefined by us in terms of keys. But the value is, of course, assignable. And the system property has the advantage that we can restrict which objects can have that property. So we can say this property can be only assigned to a cluster, and a node can have it, but only if the node has inherited it from a cluster, but it cannot be assigned to a group. We have custom properties. Those are the same, roughly, but they are per repository and everybody can freely define them, even the keys. So they are the closest to true ZFS user properties. We have native properties. Those simply allow for tree introspection. Which object type is this? Is it a part of a cluster? Is it part of a group? And on-call properties allow to assign an on-call duty. They have been modeled as a property so that the internal and the external view can have different on-call teams that will handle the problem. And lastly, we have service properties, and service properties are dictionaries and not single key value pairs, but attributes can be specified multiple times, so it's actually a dictionary of key array of value pairs. The available attributes are global as well, and they can be defined per team. So if a team has multiple repositories, they have the same services available in all of them, but every team can have a FTP service that is different for every team. And those you can attach to the tree, and the white one is the one that is user set, and then the tree has every object in it has it. You can add a second pink property that is then only visible in this part of the tree, and you can also, here is the gray one, and this one is actually overriding the green one, so in this part of the tree the green property doesn't exist, but instead you have the gray property, which is the same key as the green property but a different value. And this allows arbitrary modeling of what you need in terms of information at every point of the tree. Then we come to capabilities. So we want to support arbitrary numbers of monitoring systems, but monitoring systems don't all support the same things. There's a huge overlap, but some edge cases are different. So we say every attached monitoring system has to declare its capabilities. Those are per monitoring system, per view, and per metric. So one monitoring system can say, I can monitor IPMI something over the management network. Another monitoring system can say, I can monitor ping latency over the internal production network, and another one can say, I can monitor SSL certificate validity over the production external network. Which views and which metrics exist is again global, so that you know that different monitoring systems actually monitor the same thing. There is no required overlap between systems, and every system can also, at this step, say how many thresholds it supports for that specific metric or capability. So one system can say, I have 8 or 9 possible thresholds. Another one says, I have 2. Can both be modeled. And of course we need checks, because otherwise the whole thing would be pretty pointless. Checks are assigned to objects similar to properties. They're also propagated throughout the tree via inheritance. They then define how many thresholds you use, which alarm levels you want, at which execution interval, and by defining them on a capability, you actually say what to monitor via the metric, from where to monitor it via the view, and on which monitoring system to run it. And this then looks like this, with the check being here the red one, and then it propagates throughout the tree. But now you have a problem if you want to have the same check on all the nodes, but you don't actually want it on the group and on the 2 clusters. And for that, we have check constraints that are part of the definition. and they place conditions on the checks to become active. For example, constraint, property type native, and the native property is object type and it's node. And then only the yellow one are actually a check instance that is propagated to the monitoring system. And these two here are dormant and don't do anything. And of course, multiple constraints can be combined. Here we say system property, cluster state active. And now we say here we say this one here is the active one. It has the pink active property that I've relocated from the group. And now only these checks become active, and if that property is removed, they become dormant. If it's added here, then these ones become active, which of course also means we can add a second property, a second check that runs on cluster state inactive, but with different thresholds and different alarm levels, so we also know that the inactive backup cluster is actually working. Once we have here the active configuration, we need to roll out it. We need to roll it out. For this, active checks create active check instances. If there are no service constraints, then it's just one instance. If there are service attributes, then the system will actually build from, so a service property, as we said, can have multiple values for the same key. And the system will then normalize it, so every key has only one value, and it will construct all possible combinations and issue one check for every combination. So if you have a service with 4 ports and you say monitor this port, then it will create 3 checks for each of the ports. And these check instances are sent to the monitoring systems. Check instances are versioned. Every time something in the tree changes, it looks for it creates a new version and then compares the current version with the previous version, and if there was no change, then nothing is sent to the monitoring system. We don't do update rollouts. If there is a change and there's a new version, then we actually send the old version to the downstream system for deprovisioning, and then the rollout of the new version, which means the downstream system can be completely stateless and doesn't have to implement update statements. And yeah, it also means we implement no monitoring system specifics, and every attached system requires a slim translation layer, which in turn means the core can be independent, and we can interact with multiple versions of the same monitoring system by slightly adjusting the templating layer in between. Yeah, it can be as simple as a template system. Of course, native support could be implemented, but currently there's of course no system apart from ours that implements native support for it. Monitoring systems can use a pull interface to receive rollouts. They can also register a callback address, and then they get push notifications. And they can also combine both, and on startup use pull to synchronize what they have, and then switch to pull afterwards, and periodically switch to push afterwards, and then periodically run a pull or not and synchronize that way. Also, nodes itself can query their monitoring configuration. So one of the possible ways, and the most convenient, is the node sends the configuration service which monitoring profiles it currently has, and the reply is what to keep, what to remove, and what is missing and should be fetched. And this one is actually implemented as a puppet fact. So, preview spoiler ahead. And the person that's that wrote that is still not anymore with the company, but he's in the audience. Wave. Yeah. So as a recap, this is how the old system looked, and this one is the new one, slightly different. But we have the alarm API here, which is still available here. We had the front-end console, which is now a standalone application called Global Notification System here. We have multiple inventory systems that feed into the configuration system. The configuration system in turn configures 3 ISINGER 2 high availability setups in different data centers. We also have other monitoring systems, so around 40 of them, that also feed in the API here and also use this service. And for local monitoring, we configure the metric monitoring system, and Puppet queries the service and configures the metrics client based on that to ensure that the metrics that are to be monitored actually show up in the metric monitoring. And up here we have a sysadmin with a CLI. Yeah, and so these parts here are actually, if you've been to the Monasca talk this morning, eerily similar what they came up with to what we did. So the local monitoring system reuses existing statistics clients. We have automatic provisioning of local checks via Puppet. The Puppet module fetches and then configures the statistics client and actually sets a correlation ID tag so the monitoring system knows which monitoring profile to apply. So this is a difference to Monasca. We don't do pattern matching. So it's a difference between do we monitor what comes in or do we monitor what should come in. We import inventory data from multiple sources. We have the scriptable CLI. And the system already configures 3 different systems in 3 different ways. So here we have a template translation layer. The metric monitoring natively speaks the format from SOMA, and then we also have the Puppet fact that does the metrics client configuration. So from our current point of view, we're pretty good on delivering on what we intended to do. The future outlook. So in my opinion, classic hardware-related error monitoring will become the exception instead of bulk. Because there will be more in the cloud, there will be more virtualization, own cloud, on-premise cloud, how you want to call it. The simple fault conditions that were the bread and butter of many monitoring systems is this process running. Systemd brought the daemons tools service supervision with a vengeance. So you actually don't want to see if the process is running, but you can simply ask, is it running? Or the proper question would be, why aren't you restarting it? Ping checks were always used as, is this host available? Is this host down? You can just query the hypervisor. Because with software-defined networking, a ping check isn't the bottom of the stack anymore. For the ping check to work, there has a lot of things to work. So human notification will, in my opinion, in the future only happen for more complex fault conditions, which of course means you need more input data to detect the fault condition. A single latency measurement won't give you enough data to say this complex fault condition has occurred. So the decision stage will need access to all data sources. So you need to decouple observation from decision making, and configuring a check might happen on multiple systems. So You want one check, but you have to configure 12 data sources. And this is then the part here where we already, for one check, right now interact with 2 data sources, but having a single system that is capable of configuring multiple data sources and then relocating in the future maybe these here to basically remote metrics providers that feed into the metric API and have all the threshold and condition evaluation happening here is the plan. And at that point, we're really looking like Monasca. Yeah. The original plan was to publish the tool as part of this presentation, but I had all the required OKs a couple of months ago, so it is already available on GitHub. It is not a code dump. Development happens there, and I've closed all internal repositories. It's licensed as 2-clause BSD. Included third-party libraries in /vendor are licensed according to their license clauses, of course. But they are all permissive licensed as well. And it's currently 100% Go and 1 Makefile. But the project bus factor is a bit limited because on the core system is actually only me. And now, the slide that I added this morning, small disclaimer, the conference was too early. I wanted to present the 0.9. So the current version is already running in production in our environment, but we wrote the software, and running software you wrote to running software somebody else wrote are 2 completely different things, as every operator knows and every admin. So the version originally intended here was 0.9. It includes a lot of usability enhancements, especially for manual use of the CLI, and running this software outside of a system where it's fully scripted and automated. So, for example, depending on your personality, a CLI that only speaks JSON might be exactly your thing. Turns out for a lot of people, it's not. SOMA also has internally around 170, 150 actions that it tracks. And in the new permission system that I'm currently writing, each action can be individually assigned to permissions that can be granted. So it's a lot more flexible in terms of who is allowed to do what. In the 0.8 version, it's basically the Unix model where you are not allowed to do anything or allowed to do everything. So, well, also, I'm currently rewriting all the documentation so they don't contain company internal references. And I'm doing that with 0.9 in mind, which is of course not released yet, and nothing that works for 0.9 works for 8.5. So this is a bit of a letdown disclaimer, but the next version will be around Christmas, and I'm not meaning the Perl 6 20-year version of Christmas, but I'm actually meaning this Christmas. So if this all sounded interesting to you, check at the beginning of next year, end of this year, around Christmas, 0.9 should be done, and then a bit of release testing, regression testing, and then it will be tagged. Yeah, I'm actually a lot faster. I usually don't have slides and only a whiteboard, so I can go into weird technical details and tangents. You can, of course, we don't have a contribution license. We don't have any of those fancy CLA things right now. So if you want to contribute, just open a pull request or send me a mail. And I guess the conference stops 20 minutes early because I had too few slides. I 45 minutes, 50 slides. It sounded like a good average.
That's okay. Are there any questions?